Hello, we are Team 10. This is our junior design presentation on the entirety of the course and our individual roles of what went on in this class. The PCB design started out with the creation of schematic, which is the basic blueprint before you move on to the actual PCB layout. And we started with creating a schematic that was given to us for the voltage and current sensor. After the schematic was created, we had to assign a blueprint to each of the specific component so to match on the PCB, so it'd be easier to solder. For the currents, for the capacitors and resistors, we use 0805, and for the current sensor and op amps, we used SOIC8. And after this, we were able to implement it and then create a test bench to where we can start placing components for the layout. Some basic guidelines we followed for the PCB that helped to make it easier. We avoid placing vias too close to SMT pads and traces. We made sure to place the bypass capacitors close to associated IC chip. We kept traces as short as possible and maintain a 45-degree angle. We did not place components too close to the edge of the board. We used the power layer as much as possible, and we grouped as many related components together as possible. And we started with the most important components, such as the capacitors or the op amps and current sensor and the power pads. And then we start with the bypass capacitors, in which you place those as close to the IC chip as possible, because the point is to take the AC noise out of the DC signal. This was our PCB layout, and after we made sure all the traces and all the rules were followed, we sent it to JLPCB, and they manufactured it and sent it to us. For the calculations of the voltage sensor and current sensor, we had to know that for the voltage sensor, it was consisted of an instrumentation amplifier, and the instrumentation amplifier is consisted of two non-inverting op amps, and it connects to one differentiating op amp. We use this gain equation here to act as a buffer amplifier, which means that the gain of the overall system will be 1. We did this because we used the voltage divider at the beginning, the voltage sensor and the current sensor, to get our desired output voltage. So then we can not use the second voltage divider, as we already have the voltage we need. So then
my name is Dylan, and I'm going to talk about what went wrong with the design and how it was fixed. So in our PCB board design, as Matthew was discussing earlier, we kept the current sensor off of the ground plate, which would eliminate noise. We then kept all of the traces in 45-degree angles. All of our bypass capacitors are as close to the chips as possible. And then, unfortunately, we have a V positive trace that goes to a ground point. Doing this, unfortunately, shorts the entire board, no matter what components are on it. So to fix it, we tried to solder every component that had a V plus trace in it upwards, and then jumped a wire to each of the components, and then manually inserted a 5 volts to just take away the V plus trace. Doing this didn't help the way we thought it would. So then we decided, to build it on a breadboard and then test it as we would on the PCB. So this figure over here is the circuit that was created and built and then tested, and it's simulated and was tested and worked as it should on the PCB board. And after doing that, it worked how it should. And then we could jump wires to the oscilloscope and microcontroller to get a voltage output. And then that was it.
Hello, I'm Joshua Mewborn. So one of the main things that I had a lot of influence in during this project was the microcontroller and coding aspects. So first thing that we did is had to understand the basic background behind microcontrollers. So when you're using a microcontroller, all the little pins that you see on the board are used to output either a high or a low value. And when doing this, a logical 1 represents a high voltage value and a logical 0 represents a low voltage value. So what we decided to do was implement this and run a DAC or ADC that would change from an analog signal with infinite values to a digital signal that had a discrete amount of values. And this let us implement the code using the embedded coder. So this, the interrupts that we used were for a closed loop system. So basically how an interrupt works is it's a signal that is sent by either hardware or software to let the system know that an event has occurred. When an interrupt is triggered, what happens is the microcontroller basically jumps to another section of the code, which is called an interrupt service routine. So when that event is triggered, it jumps to the interrupt service routine, completes the code that is of there, and then we'll jump back to the original amount of code wherever you had left off. So in our case, this was our triggered subsystem, or what happened when the interrupt was triggered. So the ADC will change, it will output a specific signal from the sine wave that we want, and it will send that signal into this triggered subsystem. From there, those analog values are converted into digital values and are offset by a specific number, which is basically just a calibration for how sensitive the ADC is. So in our case, a 1880 was the constant, which was added or subtracted from the output of the ADC so that we had a baseline of 0 for our sine wave input. From there, we used a PID controller. And for this, there are 2 constants that are input into this controller. The first one is a proportional constant, and the second one is an integrating constant. And those are proportional and integral and integrating gain. And then we used an enable switch, which basically turned on or off the PID or the system. And by doing this, we could affect the output from the sine wave out into the actual H-bridge and the rest of the console. And I'll go ahead and
hi, my name's Isaac Gone, and I was in charge of lab 2-1 and 2-2, which was the H-bridge DC to AC inverter. To start off, we had to calculate initial nominal values, and these were the formulas that we used to calculate them. And this was the layout design that was given to us, and the values were plugged in to gain the results that we needed. Basically, it just switches from DC to AC. Some like applications would be hooking up a PV to it and extracting the power from the PV arrays and sending it to the grid. For lab 2-2, a closed loop layout was chosen to regulate the input power and the output power. This is a typical closed loop design where you have the reference added with the output, and then it's sent through a compensator and then through the plant. In this particular lab, we used a PID controller for the compensator. And this was the result for our PID controller after trial and error and plugging in our proportional constant, integrator constant, and differential constant. And these were our results for the PID controller results, regulating the low voltage output current and output power. And
so that's it for that's it for this group. And our main source of communication, we use Discord, and that's where we set a time for meetings and when to work on our assignments. Thank you.
You literally got you got That was some weird time.